All right, so today I wanted to talk a little, we're still in this land of random number generation. And there's some, good discussions and good questions. As far as random number generation goes, for a lot of the known distributions, don't write your own random number generator, okay? Don't try to write R norm yourself, right? You did Box-Mueller to generate some numbers from a random normal, but in real life, don't take your Box-Mueller code and try to do something. It's going to be poorly efficient. It will have poor efficiency and things of that nature. This is mostly an exercise to kind of understand this concept of random number generation coming from different distributions, as it will play an important role in the future. But at least for known distributions, we won't do this. But while we're talking about some known distributions, there are other methods for generating values from other distributions. Okay, so I think for one of your homework problems in the upcoming homework, I'll have you run a little bit of adaptive rejection sampling, and then for something like a chi-squared distribution. But let me just talk about known relationships that you can use for things, right? So we have known relationships between distributions. Can be used for random number generation. So, for example, so these relationships you should have at least learned about in like 100B, right? So we'll say, let's say you can generate Z coming from the standard normal, right? So either from Box-Mueller or some other method. Okay, so let's say you can generate Z from this. We have a lot of distributions that are based on Z. Okay, so the first one is we can just say if we just take our generations V, okay, so if we just square Z, okay, into V, then V comes from what kind of distribution? Chi-squared with 1 degree of freedom, right? Okay, what if I want chi-square with multiple degrees of freedom? What do I do? We would just do this multiple times and add them up, right? This is, let me see if I can just make sure my notes are correct here. Okay. So here, if we just square Z, then we get chi-squared. Okay. If we say S, here we'll just say Z1, Z2, Z3 are Zm are IID from normal 0, 1. Okay. If we have this, then we can just sum these. I'll say Zi squared, okay, which will be, Z1 squared plus Z2 squared. And this, if we say S, the sum of this, then S comes from chi-square distribution with m degrees of freedom. So these are, so you know, if we do have the random chi-square generator in R, but if you didn't and you just had the random normal, if you just used R norm, you can generate chi-square distribution from any degree of freedom here. Okay, so this is so these are some known relationships. I'm assuming this. I'm hoping this was covered in 100B, and you kind of recall a little bit. I know you don't deal with it on a daily basis, so it's easy to forget these things. Okay, so that would be chi-squared. Do you guys remember your t distribution? How do we generate that? What is the t distribution anyway? Yeah, it describes the distribution of your sample mean if you don't know your population variance type of thing, and so you have this slightly odd, not odd, but it's kind of if we look at how the t distribution comes about, it will make sense. So, for example, we're going to say z comes from normal 0, 1, and then we'll say v comes from chi-square distribution with m degrees of freedom. I'll say, or you can also just write this chi-square distribution m degrees of freedom. So pf equals m, and then so t will come from z divided by square root of v over m. Okay. Okay, so this is kind of like the compensation for not knowing the sorry, my brain just stopped. Not knowing the population variance, right? So we're basically, this is kind of like finding you're taking the normal distribution, and this thing, if we do v divided by m and we take the square root, this number is not going to be too far away from 1 itself, right? So this, but it makes this value, it gets wider as the thing goes, right? So your normal distribution looks like this, and then your t distribution just makes it a little bit flatter. That's overly exaggerated, okay? But where this appears, you see. Okay, so this is sample mean based on n+1 observations. Where the population variance is unknown. All right, well, it's actually a little. Okay, so we have the t distribution, and then you also have, other distributions, the f distribution, things like that. Okay, that we can use our known relationships between distributions to generate these things. Okay, I wanted to also talk about generating from a multivariate normal distribution. Okay, so we'll talk about generating values. Well, we'll just keep it simple from a bivariate normal distribution. Okay, and so the bivariate normal distribution will be so if we say that we can have x1 and x2 comes from, we'll say, normal sub 2 to indicate that it's in two-dimensional space of vector u with variance sigma. Okay, so the vector u would be kind of, or mu1, mu2, and then your sigma matrix. This is your covariance matrix, sigma 1 squared, sigma 2 squared, and then this is the covariance between 1 and 2, 1 and 2. If this is the case, then x1 and x2 are independent. And then your distribution will look, will just something like this, where they're perpendicular. But if they are, if sigma 1, 2 is not equal to 0, we'll say is greater than 0, then now you suddenly have kind of something that looks like this, and you have covariance between your generated samples. Okay, so we're going to assume we can generate from the normal, standard normal. How can we generate from something like this? Okay, so if we can generate z1 from normal 0, 1 and z2 from normal 0, 1, can we transform or or get values, we'll say from normal mean mu and all right, well, let's let's kind of explore this. And okay, so if these are just coming independently, then we can say that that z can be z1, z2, and these come from normal 2 with mean with the 0 vector as the mean and the identity matrix as our covariance, right? So this is our. Are we in agreement here? Okay. Okay, and then we will define x to be kind of a transformation of B, we're going to just add a constant B to Z and multiply some matrix A to Z. Okay, so we define X as, you know, multiplying Z by a matrix, matrix A, and adding a vector B. Okay, and what we want is we want to find the appropriate vector and the appropriate matrix so that the resulting mean and standard deviation of X will equal the mean and standard deviation that we want. Okay, so we want to find the B vector and a matrix so that the mean and standard deviation and covariance of X have the desired properties. All right. Is that okay? So we're gonna say we're gonna define this I guess this is the X vector, huh? This vector X, so that, you know, we just add a constant and we multiply it by some matrix so that the resulting thing has the properties we want. Okay, so let's find the values.
By covariance, you mean the variance covariance?
The variance covariance, yeah, variance covariance matrix. Okay, so the mean of the X variable. Okay, so this is the mean of the resulting X variable. Okay, well, this is going to be the expected value of our X variable. We've defined the X variable as the matrix B plus, and the vector B plus, you know, our random variable Z. Okay, and so the expected value of this is going to be the expected value of B plus the expected value of A times Z. Okay, and we can pull out the matrix A. And we know that the expected value of Z, this is 0, right? Because Z, again, is Z1, Z2, where Z1 and Z2 are IID from normal 0, 1. Okay, so we know that this expected value, this will just become 0. 0 vector. And thus the expected value of B, being a constant, is just B. So mu x is this. So we pick B to be equal to the desired mu. Desired mean vector mu. Okay, so whatever you know, whatever mean you want for your bivariate normal, just you set that to be the B vector that you're going to plug in to define your X. Okay, and then okay, so we can do the same thing for the covariance, the variance covariance matrix. Okay, so we have our matrix, the variance covariance matrix of X. This is our covariance of X. We've defined the covariance to be B plus AZ, okay? And you know, if you're just adding a constant, that doesn't affect the covariance, so the covariance just becomes the covariance of AZ. And we can kind of factor out the A, right? For this, I don't know if you guys recall this, but you would get A times the covariance of Z times A transpose. Maybe we recall this. Okay, and what is the covariance of Z? So Z1, Z2 is, yeah, Z1 and Z2 are IID from this. So this thing, so the covariance of Z, you know, with Z1 and Z2 being IID from normal 0, 1, this is just the identity, right? Okay, so this becomes the identity. So you get A identity A transpose, which just becomes A transpose. All right, so what this means is find a matrix A so that A transpose A transpose is equal to the covariance matrix that you desire. Okay. So this is what we're going to do. We're going to try to so you know, if you want to have a bivariate normal where you know you have covariance of let's say a 0.64 or something, you know what can we do? So all right, so there's a theorem, or there's a method called the Cholesky Decomposition. You guys heard this? Okay, so the Cholesky Decomposition, this allows us to, if we have a positive definite matrix sigma, okay, allows us to decompose a positive definite matrix sigma into a lower triangular matrix A such that A transpose is equal to sigma, which is what we want. Okay. Positive definite, so covariance matrices are positive definite, okay. So we're gonna, so a lower triangular matrix, we can say that if A is lower triangular, then what we have is, we call this T11, and then T21 and T22, and we have a 0 here, right? Okay, and this just means that I can do A times A transpose. A transpose is going to equal the matrix that we want, right? So I would do T11, T21, so this is A times the transpose of A. Okay, and we want it to equal the sigma that we want, right? So our sigma is sigma 1 squared, sigma 1, 2 being symmetric. We have sigma 1, 2 up there also, and sigma 2 squared. Okay, so this just involves some algebra, and can I just skip to the answer, or do you want to work through it? Skip to the answer, right? Yeah. Okay. Right. Huh? Yeah. Okay. All right. So it's just algebra. You guys can do this, right? So do algebra and get to get these results. All right. So you're gonna get T11 is equal to sigma 1. Okay, that's easy. And then T21, so this value becomes sigma 1, 2 divided by sigma 1. And then T22 ends up being the square root sigma 2 squared minus sigma 1, 2 over sigma 1 squared. Okay, so you just try to figure all of this out. Okay, so this gives us the values that we need for our A triangular matrix. Okay, and so, putting this all together, we said, Z is equal to Z1 and Z2, which come from normal with mean, mu, and identity matrix. Okay, basically generate two IID-Z's from normal 0, 1. Okay, and then you create X, which is equal to B plus A times Z. All right, where B is going to be your desired mu1 and mu2, and A is, I forget already, sigma 1, and then down here we have sigma 1, 2 over sigma 1, 0, and then sigma 2 squared minus times your Z's. I should have put. Okay, and then X will come from a bivariate normal with mean, mu, and variance covariance matrix sigma, which is what we want. Okay, so I can do a quick demo of this in R. In R we, I guess we'll demo this, but we have a package also in R that does it, right? Everything we can think of, probably someone else thought of it and made a nice package for us. But there is a nice R package called MVT norm, right? Where you supply it a sigma and a mu and a sigma thing, and it'll generate it. Okay, but let's try this out, and we'll take a look here. Let's okay, so let's say so we will say we want mean, I don't know, to be 1, 2, and sigma matrix, we'll say 1, 0.07, 0.7, 0.7, 1. Okay. All right. So I'll define this, and we will say mu is equal to this, and we'll say sigma will be, what do I do? Matrix of this, and row equals 2. Right? So this is going to be our covariance matrix. All right, and we're going to generate a bunch of normal things, right? So we'll do I'll do z is going to be r norm. I don't know, we'll do 1,000, okay? And then I'm going to just make a z matrix z, and I'll have number of rows 2, okay? And so now I have 500 things in my matrix z, okay? And what we can do is we can just do the there's a function called Cholesky that does our Cholesky decomposition, right? Col does Cholesky decomposition for us. I guess we could do it ourselves also, but why bother? Okay, so here's our there's a Cholesky decomposition. We'll need to transpose it because it gives us the upper triangular. So here's our lower triangular matrix, and so we'll call this our matrix A. Okay, and then and so what I'll do is we can do I can just do A times each column of Z. So if let me just take the first column of Z. Okay, and I can do A times this. Whoops. Okay, and I will get this. But I can also, let me just show you. If I keep 3 of these things, okay, it will because of the matrix multiplication, it'll give me basically 500 columns, right? So if I can just do A times Z, and it will calculate basically A times Z for every single one, okay, across the board here. So I don't have to just isolate them just to 2 by 1 column vectors, okay? So this is we can take advantage of matrix multiplication to avoid, having to make a bunch of column vectors of Z. Okay, so this will give me A times Z, and then all I have to do, I can also take advantage of R's recycling, and so I can just add the mu variable here. Okay, and so we will store all of this into our output x. All right, so all we're doing is just going to do x is mu plus A times Z. Ta-da! Okay, and then now we're done. We can so x 1 by 2, 500 columns here. Okay, so if I want to plot this, I'll probably just transpose x, and we can plot this. Whoops. And there we go. This is, I mean, this looks like a bivariate normal, and we can test to see if x has the properties that we want, right? So we can ask, what is the we're going to have to do col means, right? Column, how do I do column means of this? Okay, so that's pretty close to what we expect. 1, 2. Of course, because it's a random thing, we don't expect it to be the same. And then if we ask what's the covariance of x, okay, that's also quite close to our desired covariance matrix. Kind of within our thing here. Okay, so let's Let's see. This seems a little low. Let's see. Okay. And all right, so that generates values from the bivariate normal, just kind of using some transformation steps here. But again, let me see. Let me do library mvt norm, and we have the package, the command rmvt norm. Is it rmv norm? I don't know. Okay, so we just do r. So let me see if I can. I'll call this y. Y will be rmv norm. We want we'll ask for 500 values with mean equal to mu and sigma equal to sigma. We'll run that, and let's plot y. Okay, that also looks reasonable. All right, and we can ask column means of y. Now I'm afraid I made a mistake somewhere, and covariance of y. Yeah. Okay. So it seems reasonable here. Okay. All right. That's just more random number generation, so we can talk. Generating things from a bivariate normal, which may or may not have been obvious from generating original independent normal values. So if you need to generate values from a bivariate normal, which you might need to do, you have to take into account the covariance matrix. Okay, we'll end here. I'll post up the next homework assignment, and then I'll see you guys on Wednesday.